Right. So last lab, I gave you the basically only the sonar. You have seen the principle of calibration. This was the main goal of this sonar, okay, which is to understand this calibration graph, calibration table, sensitivity, resolution, etc. Okay, I wanted to add the potentiometer and the encoder. We had to wait for section Thursday section to finish, which was yesterday, and this means I'll try to do it today night. I will give you a video about encoder and potentiometer. These are simple, straightforward videos, and a template for the report. Okay. So this was around 7. So hang up. We have time, and we have no rush. I will update you with everything. I don't want to rush the content, and you don't understand. Okay, I can do this, but my objective is to do things slowly and efficiently. So hang on with me on this lab number 7 thing. Okay. Any question about lab number 7, the sonar specifically, about calibration, resolution, standard reference, sensitivity of the sensor? Okay, so this was this. Okay, we found the sensitivity like this, and potentiometer encoder. We said we'll do a video. Okay, so this means you're okay with that, no questions. Type. Lab number 8. This is the last lab in mechatronics, basically in mechatronics experiments, okay, which will be about DC motors. Right? Today we'll focus on DC motors, specifically the brushed DC motor. I'll explain 3 motors, but the experiment will be on just the brushed DC motor. Okay. So this will conclude the reports. This is the last week where you will have an experiment. Okay, so this is good news. Okay. Now the generic topic is mechatronics actuators. Slight or brief discussion about actuators. Let's hear from you. What is actuators? What is an actuator? Okay. I believe you must have heard about the term maybe in the lecture part. What is an actuator? Yeah, a response to a command. Okay, this is correct. It's rather generic. Okay. An actuator does the actuation. شو يعني basically in any system. Okay. Let's take an example as all right, imagine you have this mug. This is a mug, all right, but it is a heater mug, so this is a heater in general. Yeah. So you have inside the mug you have a liquid, and you want to heat the liquid. So to heat the liquid, here inside the mug you may have some coil, heater coil, like this. Okay, so this is like a heater. All right. So basically, this is the energy delivery component, okay, which is a heater coil. So your heater coil. Another example, let's see, imagine you have a robot like this. This is a rotary joint. You have another joint like this. Okay, this is here, and the end effector. Okay, now these are rotary joints. This means they rotate. Okay, now the question is, what is the element that is delivering the mechanical energy here in case of robots? Okay, in that case, this will be a motor. Generically speaking, this is a motor. All right. So these are both are actuators. These both are actuators. Okay. So an actuator is the energy delivering component. okay, in a system. Now in feedback systems, you may have a system like this, okay, and the system can have an input. This is the input. In more detailed block diagrams, where you have to show each component, sometimes the actuator is here. Okay, so basically this is the actuator, or the element that is actually forcing the system or giving energy to the system, and in order to change its state. Okay, this can be a motor, heater, hydraulic valve, and with these you have hydraulic actuators. This is a topic by its own. You have hydraulic actuators, okay, etc. So all of these are they take a command and then translate this command into energy carrying variable. So this is energy carrying. Okay, so this is a simple introduction about the actuators. Okay, can you give me an example on an actuator? Let's hear from you. Just an example that comes to your mind. Okay, doesn't have to be servo motor. Yes. So this is an actuator. By the way, we'll discuss servo motors today. What else do we have? Servo motor. Where do you find a servo motor? It's actually, you can find it in a lot of examples. Solenoid, yeah, solenoid is an actuator. True. Yep, because solenoid is a solenoid like this, and the solenoid will generate basically a magnetic field. Okay, this is magnetic field, and this magnetic field can open a valve, and it can close a switch in a relay, etc. Okay, so this can be an actuator. Servo motors, you can find them in. Who can tell me what this is? Example to find a servo motor. Yes, RC aircraft control servo. Yeah, this is nice. Okay. Right. So again, generally in these aerospace applications, you might have this. Okay, these, I don't know what they call them, ailerons or rudders or whatever. But maybe you want to, or wings sometimes. Okay, maybe you want to move this left and right by theta. Okay, this will give you a directional force on the component of an airplane. Consequently, you can steer the airplane like this. Okay, car mirrors, they go up and down, or they basically rotate like this. They go and left and right. Internally, there will be some servo motors implemented. Okay. All right. So these are actuators. We will come to these stepper servo brushless later on. Okay. So these are, by the way, all of them. These, whether servo or no, not this one, just here. They are based on motors. So there is, consequently, at the end, you'll have a DC motor inside them. Okay. Notes from your side. Yeah, they call the flaps. Okay. Right. So this is nice. Very interesting and important example on servo motors. Who can tell me what this is? Not yet. Oh, wait. It's hard to draw this. In cars, where do you see this one? The the drawing maybe not perfect, but okay. Intake throttle. Okay, sure. So you see this one. So this one is actually a throttle body. Let's borrow this image. Copy image. Okay, and this is electronic throttle body in the car. Okay, and here you see this axis or this shaft. It's connected here to a mechanism where we have basically servo mechanism. Let's call it. Let's consider it like servo. Okay. Okay, so this you'll be able to control this opening of the throttle body. Okay, based on the required speed of the car, the load condition, etc. So I think here there is the motor, and here probably this is an encoder to measure the location theta, feedback to the system, and the motor will give a command based on that. Okay, we will discuss this servo mechanism. Right. These are actuators. The definition, I think it's clear. Okay, and we have endless examples. All right. Now we'll focus today on DC motors. All right. I will not go very deep in theory. Okay, I will explain this simple principle of Fleming left-hand rule and the electromagnetic effect. Okay, this is very simple. Now we know from physics, I hope, let me put the page here. If you have a current or a wire like this, okay, and the wire is carrying a current I, and if you have some magnetic field crossing this wire, okay, from physics, let's call this as magnetic field, directional like this, and this is a current. From physics, you know that this will induce a force on that wire. Okay, so moving charges in a magnetic field will experience a force. All right. Usually the force is something like force equals I as a vector cross B, something like this. So this means by right-hand rule you have I cross B. This means that the force is somewhere like this. Okay, is that correct? The battery slow. All right. So this is the very, very basic and elementary principle behind most of the motors, whether AC, DC, brushless, servo, whatever. This is the main principle. Okay. What we actually want is to convert this electrical energy. Okay, هنضبط الأمور like this. So here we have electrical energy to mechanical energy. All right. Now this is the main goal behind these, behind the motors, okay, or electromagnetic actuators. Okay. Now how is it done? You have, you don't have this linear motors like moving up and down, but rather it's designed to make it rotary. Okay, which gives the topic about DC motors. Okay, so principle of DC motors. Let's put this in red. Okay, now here in front of me I see instead of having a single wire, I have two coils. So I have coil number one, which is just here. Okay, so you have coil, and you have another coil like this. Okay, why is it coil? Now you know if you have a generically like ferromagnetic material like this, and you have a coil. Let's put it like this. And you have a coil wrapped around this material. Okay, and imagine that you have a current here, I. Okay, what's going to happen to this material? Simply, this material will turn into a magnet. Okay, so basically here you have some magnetic field lines. Okay, something like this. Okay. Now let's assume that I have a north. Put some eraser like this. Alright, and I have this north like this. Now the north here will be blue, so I'm going to stick to that color. Okay, let me put here like north. So this means the directions of these magnetic field lines or flux lines will be like this. Right? Consequently, this is actually south, it's red, so I'm going to put a south here. Okay, now this is the main principle here. I have a coil, and here you can see there is a material or a ferromagnetic material in order to concentrate these flux lines or magnetic field lines. Okay, so here let's say this is north, and this is my south like this. Okay, of course you can imagine you have just one wire, but again this is very weak. So if you have one wire like this, okay, and you have magnetic field like this, all right, so this is very weak. Okay, so again, in order to concentrate or to amplify this effect of the force effect on this conductor is to make a wire like this here. Okay, sure. Okay, so now this one here, you have, of course, this is a DC motor. Okay, this is a DC motor, and it is a brushed one. Okay, so let me say that this is actually a brushed DC motor. Okay, which are the most commonly used motors, and they are the simplest. Okay, for reasons we'll see in the experiment. Now the physics behind them, or how they internally operate. Now here I have two conductors. Okay, this is plus, this is minus. Now I'm imagining that I'm connecting this to a battery or a current source like this. Okay, through my voltage. Okay, now when the current flows into these conductors, okay, it's delivered to these coils, and you can see here that the coils are connected together. Okay, so basically the current will flow into this coil here, continue to this coil, and come back, close the circuit. Right? Now since I have two coils only, we call this dual pole or two poles motor. Okay, so this is two poles. Yeah, I know, two poles. Okay, so this is pole number one. It's called pole, and this is another pole. Okay. All right. So what's the principle here? Now we see. Now I have a location, a generic location of this. What we call, let's call it. This is my rotor. Okay. The whole body is my rotor, which is the rotating part of the motor, and you have what you call stator. Okay, which is the static part of the motor. Okay. Right. Now, finally, the principle is very simple. Now, the stator is actually two magnets. I have a south magnet and a north magnet. Okay. Now, if the current is moving through these coils, it simply will create a magnetic field, as we have seen here. Now, this magnetic field, or the created or the induced magnetic field in the rotor, will interact with the magnetic field of the stator. Right? So basically here, knowing that this is south and this is south, what's going to happen is that this south, just a little bit, okay, so this south will start repelling this south. Okay, so this is a repelling motion. Right? At the same time, since I'm having a north here, and basically here you have a north induced in this ferromagnetic rotor, this again will create a repel motion. Right? Now this repel motion is actually creating what we call, right, خلينا نوضحها ب two-dimensional drawing here. Now this is my south, this is my north. Okay, and the rotor inside like this. Right, now you can imagine that this is a north, so actually lines are going from north to south. All right, let's just put here that you have a north and you have a south. Okay, now what we have done is we have created a south here and a north here. Right. Now this has created some repelling motion like this. So consequently, let's imagine that here you have a force, and at the same time you have a repelling force here, and this has created a force like this. Okay. Now mechanically, we know if we have two forces opposite direction, and they are both of them are moment forces, they result with, what do you call this shaft? If you have a shaft like this, a body like this, you have a force and you have some equal and opposite direction of force. They are offset from each other.
Couple force?
Couple force, exactly. Okay, so basically inside DC motors we have what you call couple force. Okay, so the couple force, if it is on a shaft, then we will call it a torque. Okay, so consequently we have a torque. Okay, sure. So of course the torque is how much? 2 times F times the distance between them times D. This is mathematically. Right? Now people in electrical machines courses will analyze this force. They'll say the force is what? The B or I cross B times n number of wires times cosine, or yeah, since this is a cross, this is enough like this. Okay, then they will say this is the amount of current times B times n times sine theta, and theta is varying. And then they will start analyzing these dynamical and geometrical entities here. Okay, we'll not do this approach from our side. We will do a systems approach. Okay, we just need to understand the principle. Now, the tricky thing is the following. Now, if you keep this as north and this is as south, what's going to happen? Now the motor is actually rotating this way. All right. So instead of theta, I'll put omega here. Okay, this is continuous. After some time, this will move to this location, and this will move to this location, south. Then what? This can continue moving until you have a critical condition, okay, which is the following. When we have this rotor like this, so now I'll drop these magnets south and north. Okay, this is critical condition is when you have the north here and the south here. Now what's going to happen? Instead of repelling, you'll have some attraction between them. Now at this location, the north is actually attracted to the south. Okay, and here you have the south attracted to the north. Okay, now if this happens, the motor will stop moving. Okay, it will stop moving. Okay, so what will happen for real if you do it? It will actually oscillate. It will go like this, go back rapidly, so it will start humming or vibrating. Okay, now to overcome this problem, all you have to do is to reverse these. Okay, خلينا نخليها الفكرة. What I have to do is solution is actually let me put that here. This is my south, this is my north, is to flip these, just to make this as south and this is as north. Okay, now from the previous motion, okay, you just imagine that this is rotating. Actually, it's not exactly at this, it's somewhere here. This is the location where you flip the polarity of your coils. Okay, now previously we had some repelling forces like this. The shaft will start moving, okay, until it reaches here at this location. You said we solved this problem and we flipped the direction of or the polarity in my rotor, and this repellent motion or repellent force will continue. Okay, and this is seen here. Okay, now this is a good location. So actually we started to see some repelling motion here. After some time, the coil has reached a point, okay, where this is actually my north and this is actually my south. Okay, and it's still rotating, but it has reached a point where the force is weakest. Okay, so this is still rotating omega. Now the critical location is here. Now if this is north, it's still north, and this is still south. Okay, the rotor is still moving omega. You can see this here in this row here is omega. Now you see here, in order to overcome this problem and to avoid this location of having south and north attracted to each other, okay, we use what you call a commutating or commutator ring. Okay, so at this point here, all right, this conductor, I can see this conductor here, will jump and will be connected to the negative. Okay, now here this has been positive and this has been negative. Yeah, sorry, this has been positive, this ring, and this has been negative. But after some time, this will be connected here, making it, I think أنا خربطت شوي. This is negative connected here, and this is positive. Okay, so after some time, this will jump here because of this opening, and it will become negative instead of positive. So this will become negative and positive. This means automatically this will become south, and this will become north. Okay, sure. All right. Now, without animation, this is not easy to understand. So what I will do, let me just give you a YouTube link to explain this commutator idea. Okay, we call them commutator ring. Okay, let me write this in the one note. Okay, these are called commutator ring. What it does, reverse polarity in order to keep the couple force or the torque. Okay, this is what you call commutator ring. All right. Let's see how they work and then state just a couple of definitions before our experiment. Okay, commutator ring. I've seen a couple of nice videos on YouTube.
If you look at
Okay, I'll just browse to the right location. Okay. All right. Is the video clear when you see it like this on Teams, or should I send you the link?
شوي lagging يعني.
طيب, I'll send you the link. If you go to this section here, minute number 4, you'll see this commutator mechanism. Okay. Actually, the overall video is 10 minutes. Okay, we have time. Okay, so can you please watch this video for 10 minutes and we'll come back. Okay, we'll come back at 3:55. Okay, now if you browse to minute number 4, you will see exactly what we are looking for. Okay, this is a nice video. Right, see you later. Okay, guys, still watching? All right. Okay, everyone, you still watching the video? All right. I hope the video made sense. It was really nice animation about.
Doctor,
Yes.
I have a question, something that
Yes.
I did not understand.
Please.
Why in the gap it switches the polarity?
Let's see where. You mean? Yeah. Let's. You mean like this?
Yes.
Yeah. So what happens is, let me go to the critical moment. Okay, so let's take this moment. Okay, let me just borrow this image. Yeah, and the same here. Let's paste that here. All right. So at this instance, you see here we have. Let's say that the current is flowing. Let me just adjust this. Yeah. Let's say the current is flowing this way. This is the current, right? Now it will go through the brush. Yes, and then go like this. Make the loop. Okay, all of this, the current is flowing this way, coming back here and continue. Good? Yes?
Yes.
Then, yes. Now, see if this is like, imagine this is positive and maybe this is negative. Now, when this rotates, what's going to happen? This here will move up to a location. Let me see that. If I can get that from the video. Yeah, let's maybe take this one here. Okay. Now you see at this point, this pole here has become here. Okay. Now it was previously it was positive. Now when it comes here, it will become negative, and this is positive. Okay. Now this means now the current was flowing from here, from this this side, this brush, inwards. Now instead, it will go from this side and come back like this. Okay. So always you have the current flowing from positive to negative, but as the ring is rotating, okay, at some instance this is actually positive because it's connected to the positive, and at another instance it is negative because it's connected to the negative. Okay.
Okay.
You see? So in that sense, I could change the polarity here. It was south north. Now it is what? I've changed the polarity of the magnet because I changed the current. Okay. And here, if you change the direction of the current like this, if this is I don't know, let's draw it separately. Just flip my laptop again. All right, where should I put that? Let's just move these things down. Oh, it's hard to move everything. Okay, so let's draw it here below. Okay, if this is your coil like this, and this is your, yeah, this is your coil now. Okay, now if current is flowing this way, we've seen that we can do this mechanically through the commutator ring. Okay, this will make the north become here and the south become here. Okay, sure. And more details, you know, because if you have a wire like this and you have a current flowing in the wire, if the direction of the current is like this, now you will have some magnetic field coming this way in circular magnetic field lines like this. Okay. Now if you have a ring or you have a coil, if you have a coil like this and you imagine magnetic the current flowing here, okay, this actually will make let's see, like this. Yeah, this will make here, this is my north and this is my south. Okay. Now this is the physics. Now I will not go deeper than this, okay, sure. But I hope you can get the idea, which is by changing the direction of the current in the poles or in the rotor itself, I can change the polarity, and consequently I avoid this this nasty condition here. Okay, I can keep the let's put that. I can keep the torque in the direction that I desire. Okay, sure. You all understand this point?
Yes.
Yes. All right, perfect. Now we have seen the necessity of this commutator ring, and basically here we use brushes to have electrical contact. At the same time, there is motion. Okay, so these were the carbon brushes. Okay, now these brushes, we know now why they are there, but they have a problem because they have friction, and consequently they have wear. This means motors, they require maintenance, require continuous maintenance. Okay, sure. So whenever you have a brushed motor, sooner or later it will these brushes will go will wear, and eventually you have to change them. You have to open the motor and change them. Some motors enable you to open them and change these brushes. Some motors don't, so you have to buy another motor. Okay, it depends on the brand of that motor. Okay, so these are important. These are like this friction and wear, and consequently the maintenance problem is just one overcome of the brushed DC motors. To solve this, they have devised what you call brushless. This is the principle of brushless. Okay, and yeah, let's put that to overcome. So, solution of what? Of these problems, the continuous required maintenance and the friction and wear. This will consume energy and reduce the efficiency of the motor. They have used a solution to that is the brushless. Brushless motor. From the name, it is brushless. It's without brushes. So how does it commutate? The principle is the same. Remember, Shahab, the principle of this okay, this force, this is what you need to create this propellant force. Let's have another color on that. This is what I need to make force and force like this. Okay, in all motors, whether AC, DC, brushed, brushless, three-phase, single-phase, all of them, you just want to make propelling force inside the motor to create this torque. Okay, now the dynamics of this force and the overcomes the technical problems, these have founded the necessity to devise different types of motors. Okay, so this is brushless and without commutator. It's without let's say mechanical commutator. It rather uses electrical or electronic commutation. This is why they are slightly difficult to analyze and experiment with. Okay, if you have time, I'll show you these motors, but we'll skip their physics. We'll skip their physics today. Okay, because of the complication of these electronic commutation. This means they require special circuit. You cannot connect a brushless motor directly to a battery. You have to have a special circuit, and we call this the driver, brushless BLDC. This is how it goes, BLDC driver. Okay, we'll come to this. Using special My writing is not the best in the world, so I have to go slow. Special driver circuits. Alright, so this is this. Okay. Kashab, so do you understand the principle behind DC motors? Anything unclear? Any point requires repetition?
Clear.
Okay. What's the percentage of clarity? 70%? Above or below?
80%.
80. Okay, that's good. Now, it's not moving well.
Doctor,
Yes.
I have a question.
Yes, go ahead.
If we turn the motor manually, do we generate electricity?
Yes. In this case, with the brushed DC motors, you will generate electricity. Okay. Why? Because here the opposite principle to these motors is you have a coil. But you know, if you have a coil like this, a big coil, and you have a magnet, let's put it as like this. You have north and you have so you have north and you have south like this. Okay. Now, if the magnet is moving, let's put this. If the magnet is moving, you know, you will induce some voltage here. You induce some positive, negative. You'll have some voltage. Yeah. And here, this is happening in the brushed motor. You have a moving coil, which is your rotor. Okay, and you have two magnets. Okay, so basically, if you rotate the motor manually, you will generate some electricity. Okay. Circuit-wise, we'll come to this. We call this VEMF, electromotive force. Okay, this is due to the motion of the motor. So this is very nice question. Now, خلينا أفتح المانيوال مرة ثانية. أعرف ليش اخترب عندي الوضع. طيب نرجع هون. Let's open that. طيب, before I continue, now I'd like to show a couple of pictures I took just now. This is here. I see this is a DC motor. This is just a DC motor. Now this is very simple. It doesn't require a special circuitry to operate it. You can just use a switch, a relay, or manually connect it to a battery. If you just want to rotate it on off. Okay, so you can put here positive, negative, or positive, negative. Consequently, here you'll have a rotational speed. Okay, now internally, let's see the brushes internally. Okay, let's go here. Now, you can see here we have two brushes. I hope the image is clear. Okay, let's comment on that. Let's open it separately. Sorry, like that. Alright, so here you see these brushes. You have okay, you have a brush like this, and you have another brush like this connected here. Okay, and basically this is a conductor going to this wire here. Yeah, this is going to this wire here, and this is going to the red wire like this. Okay, so this is an image showing the brushes inside. Okay, now where is my rotor? Let's see the next image. Yeah, one of them should be better clarity like this. Okay, now we can see here, maybe not very clear, but hopefully it's clear enough, the commutator ring. Okay, so this is basically here, this is your commutator, just say commutator. Okay, and these are my poles, so you can see here, these are your poles. Okay, you have 1, you have 2, and there is 1, 3. Okay, now you can conclude that number of poles equals number of commutator rings, or number of commutator rings. Sharp. So the image may be not perfectly clear, but each of these rings is connected, actually each of these poles is connected to one commutator ring. Okay, now obviously the higher those number of poles, and consequently number of rings will increase, the better and the smoother the motion of your motor will be. Okay, sure. All right, so I hope that was clear enough. Now, give you extra information about DC motors. Now you notice that the DC motor, sorry, circuit-wise, let's do drivers and circuits. Okay. Now, in general, to drive or to operate a DC motor, you can directly hook it up to a battery like this. Now, this is the circuit symbol of a DC motor. They just put this symbol like these two squares to give you the sense that this is a brushed motor. They usually do like this. This is the motor, and this is your voltage source. The voltage, of course, will make a current. Okay. Now inside here, when the motor rotates, your colleague has asked a question about that if the motor can generate power. Actually, this is happening when the motor rotates with a speed of omega. Internally, it will induce a voltage, what you call voltage EMF or back EMF. Okay, this is due to the rotation of the coils inside the motor, and they are crossing a magnetic field, so they will generate some EMF or back EMF. Okay. Now this is the current in the motor. Okay. Now this will operate at full speed. Okay, because here I is the maximum. You are assuming that you are giving here maybe the maximum voltage, and omega will be your maximum. Right. Now, if you want to control the current, okay, this is the control of DC motors. It's that I want to manipulate the current, and consequently I can manipulate the speed of the motor. Now, in that sense, you will need some driver circuitry. Okay, so here I can see this is a driver circuit. What is a driver circuit? Simply a driver, okay, is a circuit that amplifies voltage to drive a DC motors. Okay, so we're focusing on DC motors. Why do you need to amplify? Okay, because in often cases I have what you call a controller giving a command to a motor. Okay, so amplifies voltage, let me say, from controller. From a controller now to drive a DC motor. Okay. So a controller simply is like a thinking device. Okay, this can be basically it's a computer. Generally, we use a computer. Like maybe you have a DAC device, okay, and maybe you have an Arduino. Whatever. Okay, most motors they have a special controller. Okay. Okay. Controller that can withstand the current and the voltage. Okay. Excuse me. Now this is called edge bridge. Okay, because the principle that it operates okay, now I don't want to a lot of time on this, but let me just give you the basic principle behind this driving circuitry. Okay, this is the edge bridge. Now edge bridge, you have here a supply. It's a constant DC voltage. Okay, now you know that this voltage here will give you a current like this. If you want to reverse your current, you have to manually remove this battery and reverse its polarity and reverse the current. Okay, and now we don't do this. We use electronic circuit to do this, and its principle is very simple. Okay, if you have, imagine you have a DC motor like this, you have one brush here and another brush here. Okay, and imagine that you have one switch like this and another switch like this. You have here one switch like this, another switch like this. Okay, now all of these are switches. You can close them and open them, let's say manually for now. Okay, now if I switch, let's say this is A, B, B prime, A prime. Okay, if I switch B and B prime, if I close them, what's going to happen? The current will flow like this, from here, going like this, going here and here. Okay, let me actually close them. Okay. So if I close this one and this one only, what's going to happen? The current will flow here. Now since this is open, the current will not go here. It will go to this, go this way and this way and this way. So actually the current is going like this. Now if I switch A and A prime, what's going to happen? If I close A and A prime, okay, you are closing A and A prime. Now this is connected here. Okay, now in that case, the current will go like this, here, here, and then come back. So I've made the current go this way. So you see, by switching the proper switch here, the proper couple of switches, I can make the current go from right to left or from left to right. In that case, you can see that maybe omega is greater than 0 and this is omega less than 0. Okay. Now you already know what you call transistor. Shall you studied transistor in the lecture part? Yes, no? Yes, okay. So simply, these switches are transistors. And you have here, actually it is a FIT transistor, maybe like this. Okay, maybe another one. You have another one like this. Okay, and your motor is here in the middle. Now, why transistors? Simply because here, these transistors, you can apply a low voltage. Okay, let's call it voltage, voltage A, voltage A prime, voltage B, and voltage B prime. So by applying a weak voltage here, this is my main point. Okay, you can properly close or switch on a transistor, and an equivalent behavior of this is like switching or closing a switch. All right, so here these voltages are weak. Okay, I can get weak voltage. Why weak? Because it's coming from a controller. Okay, weak coming from a controller like your computer, because the computer cannot provide a very strong current to drive your motor. It just gives a weak voltage. Okay, and the circuitry automatically will draw the power from your power supply like this. Okay, so all of these are taking some weak voltages. Okay, this is here. So weak voltage to close a couple of transistors. All right. Okay, so to control speed using computers, they use what you call pulse width modulation. Okay, it's equivalent to switching these switches on and off in specific frequency or duty cycle, and consequently you can use a computer to control the speed of DC motor. Use a computer to control the speed of a DC motor. Okay. Now this is just for your information. I will not go into pulse modulation, and we will not focus into today. We will not focus into drivers. I just wanted you to know this is important information. In practice, is that you need to consider always a DC motor driver, or in general a motor driver, whether DC or not. Okay, which is a device that can give you enough current to drive your motor. Okay, sure. The controller is the smart device. It's the device that determines when to switch on, when to switch off, and basically it gives the signal to this driver. Okay, sure. Okay, you all understand the driver and controller? Okay, this is important because in a lot of STPs and a lot of practical projects, many students try to connect the motor directly to a computer or to their Arduino. Because we use Arduino because it's cheap, you can manipulate with it. But the problem is the Arduino cannot drive the motor directly. The Arduino is just a controller. So this is an important information. You always need a driver to drive your DC motor, or your motor in general. Okay, we'll see later on stepper motor driver. I'm going to explain a little bit about stepper motor driver. Okay. All right. So this is about DC motors. Okay. Stepper and servo. I'm going to just demonstrate how they work and their principle. But for now, let's avail the time and run our experiment. Okay. Now the experiment is very easy and straightforward. Okay. Our goal is the following. What you'll be doing is I'll apply voltage. Okay. First, we will study the characteristics of the DC motor. Okay, sure. We will apply some voltages, different voltages to the DC motor, and at each voltage I'll be measuring the rotational speed, okay, RPM, and record those in order to find the relation between voltage and RPM. Okay, you know, physically, if you increase the current, inside the motor, okay, the strength of this magnetic field interaction will be increasing, giving you a higher force. Simply, you will be obtaining a higher force here. Okay, the higher force means higher RPM, and this way, your RPM depends on voltage directly. Now, how does it depend, linearly or non-linearly? We'll see this through the experiment. Okay. All right. Now I'm going to. Let's see. I will open the webcam. It will not be perfectly clear, but that is. I think that will be good enough because we'll see a VI instead of a record this time. Okay. So let's have this here. All right. Now it tells me to open the project, run the VI, and the DC voltage should be 0. Now you know the setup here is this one. Okay, let's see if I have it here. Yeah. So this is my board now. We'll use Elvis board simply because Elvis board can generate the required voltage from inside. Here in this black box, it's not shown to us, but simply here, let's see the good color. Yeah, simply in this black box here, there is a similar circuitry to this one. Okay, and this circuit is either connected to a brushed DC motor. This is what we will consider today. This is my brushed. Here there is a brushless. Okay, if we have time, we'll introduce this. There's a stepper and there is a servo. Okay, so let's see how this works. Now the board is plugged. The same way, I'm going to actuate the power, and the hardware is ready to run. Okay. So I have a LabVIEW project here. Each motor has a specific VI. I'll open this DC motor, and you see here I have the voltage to the DC motor. I can apply a plus and minus voltage. This is the plus will give me a direction, the negative will give you another direction, and here I have the measured RPM. So there is a speed sensor or RPM sensor already implemented in the circuitry. Okay. So let me see. The VI is fairly simple. You have just a loop here, a while loop. This is a timed loop. Okay, we did not see timed loop, but it's equivalent to a loop plus delay, except that you can just specify the loop time manually here, 2 milliseconds. So each 2 milliseconds, this will update. Okay, inside, let's see how complex is that. Alright, so this is going to an FPGA, so I'm going to skip that part. Okay, it's not straightforward to explain this one. Okay, let's see if we have the, yeah, what's the brush DC motor voltage, and you have the motor speed. Yeah, where the speed is coming from. DC motor tachometer ticks. So I can see that there is a tachometer connected to my DC motor. The brushed, yeah. So tachometer. Let's see in the image, where is it? Just want to explain to you the sensor to show that there's no magic in the thing. Oh, it's not very clear, but it's somewhere here. This is what you call tachometer. Tachometer. Okay, and the tachometer simply will count how many pulses are generated from this gear. This gear is slotted, so each gear teeth will actually generate a pulse, similar to encoders, and this pulse is counted by the VI and converted to an RPM. Alright, so this is the construction of this VI. It's not really hard. طيب. شوي طولنا بالموضوع. Let's go to the steps. Alright, so I'll run the VI. Meanwhile, let's read the steps here. It says gradually increase the voltage applied by amplifier until the brushed DC motor starts to continuously rotate, and record the voltage. Okay, let's do that together. Okay, let me just do a test. Okay, now I see the motor rotating, and here I can see some RPM. Let me open the webcam. It's not going to be perfectly clear. Okay, so basically this is my motor rotating now. Okay, is the image clear? Can you see at least like the motor is rotating?
No.
Not clear, huh?
Not clear.
Okay, so this is my DC motor, and now it's not moving. I stopped the VI. Okay, so I'll start the VI like this. Now I will. Okay, so the step here tells me to gradually increase the voltage until I see some motion. Okay, this is a practical important point. Okay, so what I will do, let me increase here from this digital control or numeric control. Okay, I don't see any motion. Okay, 0.02, no motion. So now I'm giving a voltage, 0.07 volts, but I don't see any motion. Can anybody guess why? here I'm applying a voltage to the motor, but it's not moving. So you have 0.15 volts, but no motion. Why is that? Who can guess? You remember this technical problem? Does it suit? I wouldn't agree with that, because theoretically, if you apply low voltage, you will get low RPM. This is the theoretical principle. Okay, but now it's not moving. Yani theoretically, I expect it to move at very slow RPM. Okay, why isn't it moving? I already gave you the answer. Between the rings, so if I move it slightly by my hand, okay, if you go to the webcam, I'll give it a push by my hand, but it's not really moving. And this between the ring condition doesn't really happen, because they are mechanically designed to avoid this condition. Okay, this is why you have 3 poles. And 2 poles, yeah, this can be maybe. But 3 and more, this cannot happen. Who can guess? You remember we have brushes, صح? And the brushes are causing a friction against the ring. Okay, so basically, this is due to static friction between the brushes and the ring inside the motor. Okay, so here I will keep increasing 0.2 nothing, 1.2, 1 nothing, 2.2. Okay, at 2.7, it moved slightly but stopped. So I will keep raising until I see a continuous motion. It starts to continuously rotate. This is my point. Okay, so let's go back here, increase. .4, still nothing. Like I'm giving half a volt, but it's not rotating. Okay, so exactly half, but nothing. Keep increasing. Okay. It started to rotate at 0.56 volts. Okay, sure. So you see this was this instant here. Suddenly I see a motion. Okay, so it tells us record this voltage. So let's call it V0 equals 0.56 volts. Okay, sure. Can you record this on your side as well? Okay, now it tells me do the same, but reverse the voltage. So what I will do, I'll zero this. Now I'll start increasing in the opposite polarity. Of course, here in the software, I'm giving a command, and directly the circuitry is handling this, because the DAC it has analog output, and this analog output can give positive and negative voltages. Okay, and of course, this voltage will be amplified using this amplifier or bridge circuit, and eventually the motor will receive that power. Okay. Okay, let me stop the motor. Now I want to see from 0 speed. Okay, now it moves, but not that really continuous. Okay, I'll consider this as continuous motion. So in the opposite polarity, I see 0.45 volts. This is the voltage to get the motor to start moving. 0.45. Sure. Are you following? Everyone recorded the values? Okay, should we repeat this step? Okay, So I hope you understand steps 3 and 4. Now here I could find the voltage in order to overcome the static friction. Okay, so here in the analysis it says at what voltage did the motor begin to rotate. We already recorded that. Why do you think the motor does not start immediately? We know this. Okay, sure. Now, how do you think the fact that the motor does not move at very low voltages affects the performance of DC motor? Okay, so what do you think as possible answers to this one? And how does this affect the performance of a DC motor? Does it make it better or worse? What about the efficiency, performance? Of course, it's worse. So basically, here we call them brush losses. You have losses in the friction between brush and the ring. Okay, sure. So this is a hint about the answer for this one. Okay, we will come to this 1-4. Total voltage step 6 and 7. Okay, so let's proceed with the steps. Okay. All right. So it tells us here, set a voltage higher than this one. So let's put this as maybe 1 volt. Okay. And it says slowly decrease the applied voltage until the motor stops moving. So now I'm going to decrease voltage until I see that the motor doesn't move anymore. Okay. So let's do that slowly. And you can see here the RPM, or if the webcam is maybe a little bit clear, you can see the motor still moving. And I think now you can guess why are we doing this. We do it increasingly until the motor started moving, and then decreasingly, and I want to see when the motor stops moving. It's still rotating. Still it's rotating. Okay, now it has stopped at 0.44. Okay, so go V, let's call it, I don't know, V number, V6 or whatever. V equals 0.44. Okay, I have my question to you. Why the voltages are different here? This one is not equal to this one. Okay, we have to answer this. Let's see your opinions. Inertia? Let's agree. You all understand the question, sure? Does everybody understand the question? Let me give you a hint. You remember, maybe in physics, we have some mu k. What do you call them? Mu k and mu static and I don't know, dynamic, something like this.
The coefficient of friction?
Yes.
K and S, I think.
Yeah, K. Yeah, you're right. So we know that K is it higher or less than S? Yeah, dynamic friction is less than the static, huh? So evidently here, when I was increasing the voltage, the motor had to overcome a static friction. So I had to go to 0.56 volts to overcome this static friction. But now when I started from 1 volt and started to decrease, I had to go down to 0.44 volts in order to the dynamic friction to stop the motor. Okay, so this is why they are different. Okay, Shab, you understand the answer? Okay. So this is this. Now it says repeat these steps, but from negative voltages. Let's see. Now I have to go. We said we have the negative voltage to start moving, 0.45. So I have to go less than this. So let's go -1. All right, the motor is rotating the opposite way. Now we have an observation here that this RPM doesn't give me positive negative. Okay, so it's just absolute RPM. Okay. Now what I will do, I will increase, yani absolutely decrease, until the motor stops stops moving. So this will be, we expect it to be absolutely less than this, yani maybe 0.4 or 0.35 something. Okay, so I'll start increasing in that sense. Still moving. Okay, again, webcam may be clear. It shows you at least there's rotation, and here I can see an RPM, and I have to see a 0 now, or no motion. Okay, barely rotating. I need it to stop. Still moving. Okay, stopped at 0.38, something like this. So this is V equals or minus 0.38. So again, the same idea has shown up here. Okay, sure. Now in step 8, I'll fill the table. Now I have to characterize V versus omega, and I will tell you the theoretical foundation for this. But first, let's see the practical one. Okay, so here let's begin from 0, and I need to read my RPM, so I'll modify this to have a digital display. So this is not considered. Now let's see 0.1. Of course, it gives me 0, so speed now is 0. So I need you to record with me at the same time. Let's put these in red. So I have 0 RPM. Okay. Now I need 0.02. I don't see anything, so this is 0. 0.03. Still 0. Okay, remember we have to go to half volt to see something. Okay, 0.4. It's actually 0. I don't see any motion for the motor. Let's see, 0.5. Still 0. Now our voltage was 5.6, so now I will go 0.6, so I expect to see some motion. So we have a motion. Let's see how much is my RPM. This is very nasty number. Let's zoom. Okay, what's our RPM? Now I'll consider the average value here. This is a varying value. So let's take it as how much? Let's see. 150. Okay, the average for this is maybe 155. Let's just zoom in again. Okay, so I'll consider it as 155. Okay, now of course this is RPM. You have it here. This is revolution per minute. It's not radian per second. It's just RPM. Okay, now 0.7. Okay, let's zoom and see. Okay, let's take it to 190. Okay, is everyone following? Okay, then I'll go to 0.8. Okay, let's take it 230. 0.9. $265. Okay, now I'll go to 1 volts. How much the mean for that? Okay, let's take it 305. 305. Okay, now I'll start after 1. I'll start increasing by half volts, so the jump is big. So let's see, it says 400. How much? I'll take it 485. Okay, 2 volts. Okay, let's take it 660. Okay, everyone is following? Yes, okay. 845. Three volts. Then a 4 volt, and I should put 3 volts. So this is 1025. 1025. 3.5. تقريبا 1210. Yeah, 1210. 1210. 4 volts. Just clear the chart and zoom. 1390. Last two numbers, 4.5. Let's clear this guy here and bring this here. Okay, شو ناخذها هاي؟ 1570. Okay, 1570. And 5 volts. This is the maximum as per the manual for this motor and circuit. 1750. So this is 1750. Done. Okay, so I'm going to stop my PI now. Automatically it has stopped my motor and the operation. Alright, so I have a voltage versus RPM. So now this is end of experiment, and the analysis here. Okay, I have questions, but let's see. Now it says plot. We need to plot. Okay, now here it gives you an information that the motor speed should vary linearly between linearly between a speed of 0 at 0 volt and a speed of omega maximum at the maximum applied volt. Okay, so here the assumption is that V and omega are linear. Okay, and I will tell you why in a moment. Okay, so I have to plot inward. I'm not sure how this can be plotted. Maybe XY scatter. Do you know how to plot inward? I'm not really that good at it. What does it show here? Map, stock, line. What is this? This is strange. Oh, that's not access. Oh, this is strange graph.
Isn't it easier to put it in Excel?
I think it's easier, but now I'm challenging myself. I want to do, I want to do it in Word. It's supposed to be the same, right? You have X, Y scatter, and then it should work. Okay, let's go to Excel. Okay, Shab, so since I'm copying this table, let me put it in the chat. So you have an easier way to access this data, just in case recording. Okay, so here in the chat, I pasted the table so you can access it exactly as I have it here. Okay, sure. Meanwhile, if you are like, you can copy paste. I'll go to Excel, maybe paste here. I remember from Excel, insert maybe XY scatter. Yeah, this one. Okay, Shabab. So what do you think about this graph here? This is the response of my motor. Okay. Now this is voltage in the x-axis and omega in the y-axis. I think you should be able to insert labels here, but I don't know how. Okay, I'm not that good in Excel. So my question to you, is it linear or not? Is the response linear from the shape of the graph?
At first, no, then it's linear.
Why? Why here? You're right, here at the beginning until 0.5 something, you have 0 RPM, but then suddenly you have some linear curve. Okay. Now we know this region here is, what you call dead band. This is because of friction. So this is dead band due to friction. Of course, this is static. Okay. Now here, this is linearity. This is linear curve. Of course, when you have linear, what do you think we should find?
Slope.
Slope or equation. So what I will do, let me find the slope from here. I will exclude this dead band or static friction. Okay, let me just insert another graph. Okay, so this is excluding the friction problem. Can anybody remind me how to find the equation in Excel? There's a best fit in Excel, and how to find that. I think there's a way to do it. Maybe it was from here. Formula home. Maybe add a trend line, linear. Oh, I still remember. Where's my equation?
I think there says display equation on chart. Down there.
Yeah, somewhere. Oh, yes, display equation on chart. Yeah, thank you. Perfect. So now if I close, yeah, the equation is there. So what is this? This is RPM per volt, right? Of course, you have some static friction because of, you have offset because of static friction. Okay. But how to show trend line? The trend line should show, right? How to show that? It should be some option here. Display, لا بدنا لا وين الترند لاين كيف أفرجي؟ It should show somewhere. Yeah, okay. Let's increase the width for that. ليش dotted عامل لي خليه continuous. Okay, so this is maybe better. So you see, I think the data is too good because it's just like perfectly linear. Sure. So you can see that. Okay, let's take this curve and go to OneNote, add few information, and then we are done. So I'll put this in the principal page here. Okay. So here in this page, actually I want to zoom like this. Okay, the first observation is that the response, okay, voltage is a function of omega. So basically here, let me reverse this because this is omega. So my equation here is omega as function of V equals 362.48 V minus 61.103. Okay, sure. Now I know the following from theory. This is the interesting fact that I wanted to tell you, is that omega so now the voltage and omega are related through this equation. Voltage equals what we call K omega times omega, like this. Okay, and we call this motor constant. Okay, this is my most important relation today, is the motor constant relation. It tells me simply that if you apply a known voltage through this relation, you simply can't find omega. Okay, through this relation. Okay, now the motor constant is a parameter that is given in the data sheet of the motor, given parameter. Okay, now to add to your information, it's the same for the torque. The torque that is generated in the motor, you remember that we had couple force, and this couple force will generate a torque. Now this torque is given to me as what you call KT times the current in the motor. I think I made some mistake here. Yeah, I think omega should be equal to K motor times V. Yeah, I think this is the right relation. Okay, so sorry for this mistake. Okay, so these two relations are important. Why? Because they simply relate mechanical and electrical variables. Okay, so here it says if you know V motor, just multiply it by this Km and you'll get omega. Okay, now what's this value? This is actually, I have experimentally found my Km, the motor constant. Okay, sure? You all understand these details? Where are you? At least say yes. This means no or yes? Okay, so basically my experiment was straightforward. I just applied voltage, measured omega, plot, get my equation like this, and this way I have found the motor constant. Okay, now let me just give you an interesting fact. It's very, very useful fact. In a motor, okay, this is about motor constant. Okay, motor constant, and basically we wrap up our lab today. You know the following. Let me just give you the motor like this. Two brushes. And in general, let's say I have current should be orange. I don't know why. So this is I. Okay, so what do we have? In the mechanical side, imagine that you have a shaft like this. And you have a load. Okay, this can be a pump, this can be a fan, this can be many loads. Okay, I'm putting it as inertia. This inertia is rotating by some omega, and there is a torque on that side. Okay, sure? Now here I'll say that I have the V motor. This is the motor voltage. Okay, so now I have two sides. I have electrical side and I have mechanical side. Now we know that the power in mechanical should be equal to the power in electrical. The power in mechanical is what? كأني عكست. So the power in electrical should be the power in mechanical. Okay. In electrical, the power is I motor times V motor, which equals to torque times omega. Okay. Now I know from these relations that torque equals the motor constant times the current. Yeah, the torque is just scaling, direct scaling of the current. So here this is Kt times I, and omega here is the voltage constant Km times V. This equals I times V. Okay. Clearly here you see that this will go with this and this will go with this. Okay. So you have 1 equals K, the torque constant times the velocity constant, which means that the Kt is equal, I put M here or omega. Yeah, M, so I'm going to keep it. Okay, so K torque is equal to Km. Okay, so here, if you know this K, your motor constant, which is here, and you know your current, simply you can find your torque. Okay, so it's easy to control the torque of these DC motors. Just control the current through manipulating voltage. And you know the relation, and we can find it experimentally. So this way we have actually nailed this DC motor. It's just by finding this constant. Give me the constant and I'll tell you by measuring V or I. We know how to measure V. Measuring V using a DAC or measuring I using a DAC. Simply I can find my torque and omega. Measure them or control them. Kushab, you agree about this point? You all understand? Okay. Now here I just want to add a last comment on this step 1.4. It says shows an excerpt from the brushed DC motor datasheet. So here we have some given information about this motor. Now here it says torque constant. It says in that sheet it is 238 of G centimeter over ampere, something like this. I think we need to convert to compare with our constant. We need to convert this one. Now this one is in RPMs. So in order to convert it, we need to convert the units here. The units are, what are the units here? Let's see. RPM per volt. Yeah. So if it was torque, it will be what? Newton meter per ampere. This is the unit. Okay. Now we need to convert this to gram centimeter per to gram centimeter per ampere in order to compare the two values. All right. So even if they are not equal, it's fine. Okay. For me, from my side, I trust this value more than the one given in the datasheet, simply because these are theoretical values. They are not. They can change with time, because the strength of the magnet inside the motor can change, and basically this is just factory value. It's not practical. Okay, but taking this value, now it says what is the torque that corresponds to the static friction. Can you answer this one? simply here, if you consider this constant, now, and consider the resistance of the motor. Now I know, okay, the motor has a coil inside, and this coil can be seen as a resistance. To overcome friction, I have to have 0.56 volts, all right, which is measured value here. Okay, so I need 0.56 volts. This means how much current? Okay, given that my resistance here is 21.24 ohms, this means the I to overcome the friction is 0.56 over 21.24, which is, see now I'm controlling voltage, and consequently the current is induced. Okay, so 24, this is here. خلينا نضرب بدون ما نضرب. Okay, so this is 26.365 milliampere. Right, now I know the torque is equals to K motor times I. Now if I is the friction or current to overcome friction, this means the torque to overcome friction will be equal to, now I'll use this value here, 238.94 times 26.365 milli, and then you'll find your value. Okay, so this way I found how much torque the static friction can be causing, okay, and the torque to overcome that static friction. Can you understand this answer? You basically are solving the report together now. Okay. Now this one, at what speed should the motor theoretically be moving when it overcomes the static friction? I'll leave to you. Okay, same way I can answer. All of them considering this constant, this torque constant. Okay, last question is this: how do you modify the applied voltage to make the motor behave more linearly? Okay, now this assumes that you have considered this curve, the dead band curve, okay, including this portion here. Okay, in that case, you'll find some nonlinearity maybe in your curve, and that equation will be a little bit different. In general, how to change the voltage to make the motor behave more linearly. Okay, this is similar to calibration. It has the same way as to calibration. Tasha, so let's see. Now, this is all from my side. Now, these stepper and servo, we don't have time to explain them today in depth. I'll try to give you a video or make see if there's. I think YouTube there's like better animations. To give just a hint about these stepper motors. Okay, the stepper and servo, they are really easy. This is a servo here in. I opened here in the lab. You can see the servo is simply a DC motor. This is a DC motor, very simple one. This one is potentiometer used to measure output angle, and it's actually both driver and controller integrated into one circuit like this. So the servo is a system, actually, it's not a motor. Okay, simply here the output DC motor is connected to this gear train, and there's some gears inside the motor. Eventually you have this output shaft. Okay, by measuring the location of the output shaft, the controller, the feedback circuit actually, will convert a command given through this pulse time that will convert it to a location and maintain that location. Okay, so a servo motor, it's a feedback system. It's not just a motor. It's a DC motor plus feedback. Okay, they have like this. All right, let's see. Any question or note from your side? can take attendance. Now what you need to submit is actually answers for all of these questions in the analysis section here. Okay. Now attendance. This means we can stop record.